motivation. The motivation behind this work is that the most commonly used flight controllers like Pixhawk and other widely used flight controllers, they are well tuned for well established airframes. For example, we have Alibro X500 and DJI F50. They are well tuned for these commonly used airframes, but if you do any change in the structure, the airframe, the propellers of the motors of your multirotor, the performance of the controller would degrade with comparison to the nominal controller. So there's a need for retuning. And the tuning of these controllers for multirotors are quite a challenging task, and trying to retune them through trial and error is really hard, because you want to actually implement it on your quadrotor, and if you crash, so you are going to need to cost more money on repairs and other problems. There are some limitations on model-based approaches. For example, there are some dynamics that are really hard to model. For example, the vibration effect of the motors on the structure, or fluid dynamics, the effect of propellers, the well-known ceiling effect, the ground effect. These are really hard to model. So the design for model-based approaches face these challenges. Some of the data-driven methods that in the literature have been done on multirotors, we can mention RL and evolutionary optimization methods. So the problem that they have is that the RL methods, they are heavily dependent on simulations. They need, for example, if you want to learn a policy for being able to do a stabilization and trajectory tracking of your multirotor, you need to learn it through hours of training, and so it's not efficient, and it's quite time consuming. So there is a motivation for learning a proper policy only in one iteration, in a single shot, without going through many iterations, without the need for a prior stabilizing controller, just learning from almost nothing based on the input-output data. And in this work, we want to show the application of continuous time retrospective cost adaptive control to multirotors flight control. And because we are using a continuous time controller, we don't need to deal with discrete time controllers problem. The discrepancy that there is when we want to implement a discrete controller for a continuous time plant. And we wanted to do this application in a transfer learning framework. So we do the learning in a really simple 12 DOF degree of freedom simulation, and we just move what we learned in the most simplest case to a more realistic simulation, and finally on the hardware. So considering the transfer learning terminology, we name the simple simulation as a source environment, and the target environment would be the real-world hardware and outdoor flight experiments. As we mentioned, the commonly used flight controllers like Pixhawk use fixed gain, fixed rate controllers, as shown in this figure. This is the flight control architecture for Pixhawk flight controller. As you can see, there are two main controllers, the outer loop position controller and the inner loop attitude controller. As you can see, the rates are fixed and the gains are also fixed. So when you mount your flight controller on the airframe, you choose the airframe, and all gains are pre-tuned. So in this work, we do a learning-based control. We have a learning environment. We use the really simple 12 degree of freedom model of a rigid body as the source environment for learning proper control law. And we use the continuous time retrospective cost adaptive control for learning a control law based on all the input-output data. And then we transfer the learned gains to the target environments. So we use a validation environment, which is a realistic model provided by MATLAB. It enables us to do hardware in the loop and software in the loop validations with Pixhawk flight controllers. And finally, we transfer the learned controller to the Holybro X500 and we perform output like this. We start by 12 degree of freedom rigid body dynamics. This is our source environment. We do the learning process there, and it's the most simple model with the least amount of knowledge. Then we transfer what we learned to a more realistic model that includes actuator dynamics, sensor noises, the communication delays, and it enables us to do the hardware in the loop simulations with the Pixar flight controller and also software in the loop. And finally, we move what we learned to the physical quad rotor. Another contribution of this work is the development of a framework for the Pixar controllers. So in Simulink, we can design controllers and or adaptive methods, and being to seamlessly, without any problem, transfer the controller to the physical system. So we are considering the conventional flight control architecture, and so we have an outer loop position controller and an inner loop attitude controller. The mission planner sets the desired trajectory for the multi-rotor, and the position controller, the output of the position controller would be the net thrust and the set point for the attitude controller. And attitude controller has to regulate the attitude of the multi-rotor. As for the measurements, we have attitude and rate measurements, and also position and velocity measurements. In this work, we are going to use CTRCC. I'm not going to delve deep into the method itself, just a brief description of it. So any linearly parameterized control law can be written as a regressor matrix times a gain vector. We define a performance variable that includes output error and filtered data. And we define the cost function, which is an integral over time on the output error, the control signal, and the gain vector. And the objective is to find a set of gains that minimizes this cost function. The controller that we are going to use is a cascaded PPI controller, but as we said, CTRCC is applicable to linear controllers. So if we use the usual PPI controller, the problem is that we cannot write it as a linearly parameterized controller because of the nonlinearity that arises in the multiplication of the inner loop and outer loop gains. So we add the feed-forward term, and by doing this, we can easily write it as a linearly parameterized controller. So the regressor is just the outer loop error, inner loop error, and integral of the inner loop error. And we need to learn three gains for each controller. So the learning process happens on a waypoint command and also a helical trajectory command. As you can see, the figure on the left shows the waypoint command. The multi-rotor is commanded with a step response on X, Y, Z, and all controller gains are initialized at 0, and they are getting learned over time. So we have 3 controllers for the position, the outer loop architecture, and 3 controllers for the inner loop. So in total, we have 18 gains that need to be learned. So that's why we mentioned that tuning these by trial and error is quite time consuming and hard. And figure F and D are showing the controls, the net thrust and moments applied to the multi-rotor. The figure, the column on the right is showing the learning process on a helical trajectory command. So as you can see, the figure A shows the position of the multi-rotor. It is being able to follow the harmonics on X and Y, and also a ramp command on the Z-axis, which replicates a helical trajectory command. And you can also see how the gains are getting learned in a single shot, one iteration, without needing for a prior stabilizing controller. And these are the set of learned gains. So we transfer the same exact gains to the realistic simulation and the experimental setup. So here we can see the results for the realistic simulation, and by the realistic simulation we mean a simulation that considers the actuation saturation, sensor noises, and also the integration with the Pixar hardware. You can see that in figure A, which shows the position of the multirotor, it's being able to follow the waypoint command, and on figure C and D, we are showing the output error on a logarithmic scale. The errors are keep decreasing. We have the error on the position, also the attitude parameterized by Euler angles. And figure E and F are showing the applied control sequence. And figure on the right is showing the experimental results for Holybro X500. So we performed outdoor flight tests, and we commanded the Holybro X500 to hold its position, which represents a waypoint command. As you can see, the error on position and also Euler angles on a logarithmic scale, they are decreasing, and the multirotor is being able to hold its position. Here we are showing the results for trajectory tracking. We commanded the multirotor to follow a helical trajectory. The figure on the left is showing the realistic simulation results. As you can see, we are showing the position of the multirotor on a 3D space. It's being able to follow the helical trajectory, and with the downward side, the viewpoint also showing the results. And the column on the right is showing the results for the experimental flight test, performed outdoor flight test, commanding the Holybro X500 to perform a helical trajectory command. So as you can see, when it comes into the real-time experiments, we don't get as nice results in the simulation. It's because of the nature of the physical experiments and outdoor flight tests. So when it comes into outdoor flight tests, we are dealing with outdoor conditions like a windy condition and other problems that arise in kind of experiments. So here I'm showing you some videos. The first video shows the learning process. As you can see at the beginning, the quadrotor is a bit jittery, moving around, not really being able to follow the trajectory, but after some time it learns how to stabilize its attitude, and also is being able to follow the helical trajectory. So all the gains are initialized at 0, there's no prior stabilization controller, and the learning happens as the quadrotor moves. So after doing the learning process on the most simplest case, we transfer the set of learning gains to the physical experiments and outdoor flight tests. So in this video, we are showing the position hold response of the multirotor. So we performed the outdoor flight tests, and the objective is for the multirotor to go to a waypoint and